Okay, good morning everyone and welcome to the Astrobiology Australasia meeting 2020. I'm Anna Wang, I'm an academic at UNSW Sydney. So to start off, I'd like to acknowledge the Wongal clan of the Darug tribe, who are the first inhabitants and the traditional custodians of the land that I'm currently speaking to you from. I would also like to pay respect to the elders past and present here. And because we are meeting across many nations and lands, I would like to acknowledge the traditional owners of the lands we are all meeting from and extend my respect to any Aboriginal or Torres Strait Islander people joining us today. So this AAM, for short, is like no other. AAM started 10 years ago as an initiative of the Australian Centre for Astrobiology. And since then, it's been broadening its geographic reach. You can see it started off in Sydney, in the host institution of the ACA, and then it went out to Perth and then New Zealand. And as you can see, 2020 was originally the year in which we would first hold AAM in Asia, jointly hosting with the Earth Life Science Institute, also known as ELSI, in Tokyo. And that idea was born out of appreciation of the amazing astrobiology work that's happening in Asia and wanting to form closer ties within the region. So through many discussions between our ACA director, Professor Martin van Kranendonk, and the Vice Director of ELSI, Professor John Hernland, and then myself in discussions with Mary Wojtek, John Hernland, and Tony Jha, and many others at ELSI, we became super determined to hold AAM in Tokyo. And, you know, we're all in our homes right now, and we're kind of all over the world. So I guess this has gone even bigger than we originally anticipated. So if you look in the Zoom chat, you'll see that our conference logistics organizer, Erica, has posted a link for a website called Padlet. So it's a map of the world and you can click on it. Please use the password astrobiology or lowercase and just let us know where you're from, because it's pretty amazing how international this conference has become. And we'd like you all to put a little pin down on the map, show us where you're from. You might discover some new neighbors. And put in a little picture. It could be a selfie or your pet, anything you want. So I think that's a really nice sort of souvenir and for all of us. And so although we're all sitting in our homes or offices, which isn't quite the same as gathering in Tokyo, we're super thrilled to be having people from all across the world come together to share our love for astrobiology and also inspire the next generation of astrobiologists and engineers. Our hope is to provide a supportive platform for everyone across all career levels to present their work and build networks within the greater community. So please enjoy the talks and please also use our Slack channel. The link, if you haven't already joined, is posted in the Zoom chat, and it's also in the reminder emails that you got about 14 hours ago. So the Zoom, the Slack channel will be a good way to keep in touch and continue discussions, just like you would at an in-person conference. So I would like to just quickly thank the original scientific organizing committee, you know, including those in Japan, including Tony Jha, Sean McGlynn, Yoshihiro Furukawa, Kyoko Akiyama, John Hernland, and last but not least, Mary Wojtek. And you'll see the photos here of the Sydney Scientific Organising Committee. You'll see our names in Zoom as well as in Slack. Feel free to reach out to us with questions throughout the meeting. And an extra huge thanks to Dr. Erica Barlow. She's been our logistics coordinator, absolutely amazing, and has really given the push to make this meeting happen today. So without further ado, let's start our very first session with our very first speaker. We are super honored to have Dr. Mitch Schulte from NASA headquarters open the conference for us. Mitch, I'm going to stop sharing my screen now. If you would like to start sharing yours, that would be great.
Okay, first, can I get a sound check to make sure everyone can hear me?
You sound great. Thank you so much.
Perfect. Okay, let's see if we can do this.
Yeah, so while Mitch is getting ready, just a reminder that you can ask questions using the chat function through the talk. We'll field the questions at the end and read them out to the speaker. If you like, you can also use the raise hand function in Zoom and we'll call on you to unmute yourself during Q&A. There'll also be an 11-minute reminder for the speaker during talks. So Mitch, feel free to take it away.
All right, my computer is not letting me share, so give me 1 second. Okay.
So Mitch is joining us from the US. It's well past his normal work day. So we're really grateful for having you join us.
Okay. Okay, I see. Sorry, my setting was not correctly set up here to do this, so.
Oh, that's totally fine.
Should just take a second.
This is giving a chance for, you know, participants to come and not miss the start of your talk.
Right.
It's good.
All right, let's try this again.
Fantastic.
All right, so can you see it in display mode?
It looks perfect.
Excellent.
Thank you so much.
So I know I'm now short on time, so I will try and get through this relatively quickly. As you all know, NASA has just sent on its way to Mars another rover, the Perseverance rover, which was named through a contest among school children here in the US. This for a very long time has been known as the Mars 2020 mission, and the rover now has an official name of Perseverance. So this is the official mission logo. I am the program scientist at NASA headquarters in Washington, D.C. for the mission. So I just want to go through very quickly what the plan is, maybe show you some pretty pictures, hopefully. Hopefully some of you got to at least see the launch online. I know it was very late for you guys in the Asia Pacific region. It was early in the morning here when we took off, but everything was streamed live because of the pandemic. There was very, very limited attendance at the actual launch, including myself. I was not allowed to go, unfortunately, but there were photographers there to take some fantastic pictures. So I want to show you here are some things leading up to the launch. The very top left is the rover in the clean room at Kennedy Space Center before they buttoned it all up. You can see it still has all of its lovely coverings and everything on it here. Everything is all mounted and ready to go, and so they were just doing some final testing. If you were able to participate in the Send Your Name to Mars part of our mission, your name is on its way to Mars. In the lower left here, you see mounted on the bridge across the top of the rover, these 3 chips in the top left-hand corner. Those contain on the order of, I think, 10 million names is what they ended up with, which is why we have 3 chips there. Those have all been etched onto these microchips and bolted onto the rover. So if you got your name in, your name is on the way to Mars. The picture in the middle here is as they were stacking all the parts of the vehicle. So you see the rover itself tucked inside the back shell, which is attached to the cruise stage. And then this is just before they put the heat shield onto the bottom of the rover. After they do that, they do the stacking there, and then they put it into the fairing. So this is the picture of the fairing having been put together. So the spacecraft is encased in the fairing with our lovely mission logo on it here. This was right before they lifted this entire assembly onto the top of the rocket. Which of course is an Atlas V. And so after everything was assembled, the bottom right picture here is the launch vehicle with the fairing at the top, which includes the spacecraft inside. You see the solid rocket boosters, and then this is them rolling the launch vehicle out to the launch pad the day before the launch. So this happened on Wednesday. Took a lovely shot of it during Wednesday evening here as nighttime was falling. So that's what that picture is there that you see. So for those of you who are familiar with the mission, I just want to go through this quickly. The launch, of course, this is a lovely picture of the vehicle taking off of the launch pad. So this is actually Mars 2020 on its way. The launch date was 30 July here in the US. It will take about 7 months to get to Mars, and it will arrive in February of 2021. So this graphic here shows you the trajectory that it's taking. You'll see here this first maneuver, the TCM is it's a course correction maneuver that we do. When we first launched the spacecraft, we actually aim to miss Mars, just in case anything goes off nominal, as we say. So we do have to correct its trajectory as it flies. That trajectory first correction was made, and everything went fine and smoothly with that. Everything is totally fine for Perseverance to arrive in February. The entry, descent, and landing will occur on 18 February here in the US, which will be 19 February for you guys. We'll use the same sky crane system that the Curiosity rover used. We will actually have a fairly small landing ellipse. So this graphic was made before they really did a lot of work to narrow down that landing ellipse. So we'll actually probably be able to do a little bit better than this, but we'll use the same system to land Curiosity on the surface. Once we're on the ground, we'll have the capability to traverse about 20 kilometers across the surface. Obviously, we hope to be able to do better than that if push comes to shove. We have qualified everything, all the hardware, to 1.5 Mars years, which is about 3 Earth years. So everything is sort of guaranteed to last that long through all the testing. And then, of course, our objectives are to seek signs of past life, do geology, and very importantly, collect a cache of samples that we are hoping to bring back. So I want to give you a quick panorama here, a montage of some of the great pictures that they took of the vehicle launching. So just for your reference to see what everything looked like, some from fairly up close and some from fairly far away, but pretty spectacular pictures. Of course, there are videos online of the launch if you missed it, so you can relive it if you choose. Quick update on the objectives. These have not changed since we started this mission back in late 2012. Again, first thing you do when you land in a new field area is case the place. So we want to do some significant geologic exploration, understand the environment where we are. And I'll talk a little bit more about that in a few minutes. We really want to understand the processes that led to the rocks that we see where we land. Very important second objective is to search for signs of past life. And it's very important to note that we are looking for evidence of past life. We're not looking for Martians crawling around on the surface today. We are looking in the rock record for life that might have left behind, much like we find, of course, in the Pilbara region in Western Australia, 3.5 billion-year-old rocks there that contain these lovely stromatolite forms, very convincing evidence of ancient life here on Earth. It would be great if we found something similar on Mars. As I mentioned, a very important part of this is to prepare a returnable cache of samples. So we have the capability to collect about 40 samples. We have 43 tubes on board. This will include blanks. So we, of course, want to take witness blanks to make sure that we understand any contamination that we brought with us and are able to subtract that out of any signals we get back when we get these rocks back. We're hoping to collect on the order of 20 during the prime mission, but we're going to take our time and make sure that we collect rocks that are worth bringing back. We want to make sure we include some diversity there to sample various kinds of terrains, various kinds of rocks. It'd be great to get an age date on the area, that kind of thing. Sedimentary samples, of course, which might contain that evidence of ancient life. And then finally, we're preparing for human exploration. So you'll see in the instrument package that we have a couple of instruments on the payload to help with human exploration when we finally decide to get Mars out there. So this is a graphic of what the rover looks like and the 7 scientific instruments that were selected to fly. The 2 that are related to human exploration are META, which is a weather station, and MOXIE, which will be producing oxygen out of the carbon dioxide atmosphere using the resources at Mars again, eventually to help humans not have to carry everything with them and to be able to live a little bit off the land. The rest of the payload, of course, is designed to interrogate the surface materials at Mars on scales all the way from kilometers down to sub-millimeter. And I'd be happy to talk about that some other time. I know I'm running short on time here, so I will try and get through this. I'll be happy to answer any questions about the instrument payload if they do exist. So the landing site, of course, is Jezero Crater. Here's where it is on Mars, on the edge of Isidis Basin, which is a large impact basin. This is the crater itself, which once contained a lake. There's an inlet valley and then a delta that formed just inboard or inside the lake of this, this inlet valley. And then there's an outflow channel on the other side as well. Our landing ellipse is here on the eastern edge of the delta. So to give you a little bit closer image of what this looks like, again, here's an outline of what the delta looks like, and here's where our landing ellipse is. So we're looking at a fairly safe place, although we're hoping to get fairly close to the delta so we can really start looking at those rocks right away. This is an image taken from orbit of what the delta looks like, and it's a beautiful delta. And so through some mapping, we can see some of the kinds of minerals that we see from orbit, including some magnesium carbonates along the edge of the shoreline here. So these are also very attractive targets for looking for evidence of past life. So I mentioned that we'll be collecting samples that we're hoping to bring back. So we are here with Mars 2020, which will be collecting the samples. We're currently working with the European Space Agency primarily on a set of missions to launch no earlier than 2026 to go retrieve those samples and bring them back so that we can study them here in laboratories on Earth. The NASA part will contain the Mars Ascent Vehicle, which will be the rocket that will lift them off the surface. And that will be inside an orbiting sampler. So the container will contain the samples. They'll be put on the rocket, launched into orbit, and then the European Space Agency is working on an orbiter to capture that Oz, as we call it, and bring it back to Earth. So some sample science objectives for those samples that we bring back. I won't go through this in any detail unless there are questions, but clearly there are a lot of questions we have about Mars that we'll be able to hopefully finally answer for the first time through these samples that we're going to bring back. So with that, I'll remind everybody that Perseverance lands in February, so stay tuned for that. I'm sure that will be a worldwide broadcast as well. You can find everything you need to know about the mission at mars.nasa.gov/Mars2020. And of course, the Mars Exploration Program has a lot of great assets at Mars. You can go there for more information about the sample return campaign, as an example, just at mars.nasa.gov. And with that, if there's time, I'll be happy to take any questions.
Oh, amazing. Thanks so much, Mitch, for giving us an overview of the excitement. We're all going to be glued to our seats in February. Yeah, lots of happy tears then. So we do have time for a few questions. So the first one's from Rishi Rajendra Gandhi. And the question is, how would you rule out contamination by our older rover?
So we're sending this mission to a very different place on Mars, and it would be unusual to have any of the assets that we've already sent there be responsible for any contamination just because they're so far away. We're more concerned about contamination that we bring with us on this mission. And so that's one of the reasons that we're going to make sure we collect witness blanks so that we can track any organic material that may be coming off of the spacecraft parts and things like that as they degas, as they flies to Mars and lands and anything like that. So we will be taking witness blanks to keep track of that contamination. And of course, we clean the spacecraft really, really well. It's one of the cleanest spacecraft, especially the sampling parts, that we've ever sent to another planet.
Oh, amazing. And just time for one quick question. And then if you could answer the other question in chat, that would be great, Mitch. So
Sure.
Has there been any target sites selected for Ingenuity?
Right, so I didn't talk about Ingenuity. Ingenuity is the Mars helicopter that is tagging along for the ride. And so the current plan for Ingenuity is to, it's bolted to the bottom of the rover. So it's on the underside of the rover. Once the rover lands on Mars, Ingenuity will be lowered to the ground, and then the cables that are connecting it to the rover will be cut, and the rover will drive away to a relatively safe distance. and then the Ingenuity will be able to do its flights. So the first thing that we'll do is drive the rover as best we can with Ingenuity attached to it to a place where it would be safe to fly the helicopter. That's going to partly depend on where we land, but we're not going to just want to dump the helicopter anywhere. We're going to want to make sure it's in a safe place for it to do its tests. But we haven't selected that exactly yet because we haven't landed yet.
Ah, okay, fantastic answer. Well, thank you so much, Mitch. I know there might be a few more questions in chat, so if you could answer those quickly before you go to sleep, that'd be great. But yeah, thank you so much for an amazing start to the conference.
Well, thank you guys for letting me go first. I appreciate you being accommodating for my time. Appreciate it. Thank you.
Oh, it's also a super exciting topic to start on. So thank you. And now I'm going to have Nicholas Rattenbury take over. So I believe that Nicholas is joining us from New Zealand. And the talk will be about discovering exoplanets with the Nancy Grace Roman Space Telescope. So Nicholas, take it away.
Hi there, thank you very much. I hope everybody can see my screen. So the title, as suggested, is Discovering Exosolar Planets Through Gravitational Microlensing with the Nancy Grace Roman Telescope. And this sort of represents an evolution of how we discover extrasolar planets using this gravitational technique. A little bit about myself. I'm the current president of the Royal Astronomical Society of New Zealand, a research fellow at the University of Auckland, and senior lecturer in the Department of Physics. And I'm also getting more and more involved in working with space systems at the University of Auckland, preparing ourselves and our students to take advantage of our local launch supplier, Rocket Lab USA, for easy access to space. So I have a talk on Friday about this work. But today, I am talking about gravitational microlensing. This is a planet detection technique where we utilize the effect of gravity in accordance with Einstein's general theory, where light from a background star, I'm not sure if you can see my cursor, but I'm waving it around this yellow dot here. Light from a background star gets gravitationally lensed by the gravity of a foreground object, in this case, shown in cartoon style of a star plus a system of planets, getting focused to here, to our telescopes here on Earth. This is a diagram of what's happening, of this process happening in our galaxy. This is us on Earth around our sun, 2/3 the way out the galactic disk, staring towards crowded fields of stars towards the center of the galaxy. And as everything is in relative motion, by chance we have a background star, foreground object in its planetary system, and us all line up almost precisely so that this gravitational lensing effect occurs. What we look for is time-dependent amplification of light of this background star by the gravitational potential well of this foreground object, and we look for glitches. And those glitches could indicate the presence of additional masses in that system, in other words, planets. We do this from New Zealand, and we've been doing this for the last 25 years. The trick is looking at crowded fields of stars. You need to look at millions of stars night after night, looking at the same stars, looking for this time-dependent amplification of light as things by chance all line up just right. So we are observing with New Zealand's largest telescope down at the University of Canterbury Mount John Observatory in Lake Tekapo. And there's the dome that in which this telescope resides, the 1.8 meter mission mirror telescope, and this is the survey instrument that we use to make these observations. So I'd like to just show three microlensing events which we have discovered planetary systems, and just discuss why they're particularly interesting. Well, the first one here is shown here. This is what we're looking for. We're looking for deviations away from a smooth symmetric light curve. This is amplification. This is, again, that background star appearing to get brighter because of a foreground object passing between our telescope and a background star. This is time along the bottom. And if there was no planet in that system, then all these data would line up along that cyan dashed line. But we can see that they're very clear deviations away. This is the first planet discovered using this technique. And with follow-up observations using Keck, with the HST in this case, we're able to get some information about the star that the planet is going around. Using all this information, we're able to say that this the perturbation relates to a 2.5 Jupiter mass planet, which is orbiting about 4.3 astronomical units away from its red dwarf host star. The first rocky planet, so moving away from gas giant planets, discovered by microlensing was this one here. Here you can see the deviation is this little bump here. If there was no planet, the data would all line up on this yellow dashed line. And this one was a 5.5 Earth mass planet orbiting about 2.5 astronomical units away from its red dwarf host star. So this, at the time, set a record for the lowest mass planet found to date. And what I find particularly interesting, this event was a discovery of a solar system analog. So essentially a scaled down version of our own solar system to at least the Jupiter and Saturn masses. So here's our solar system, obviously. What we saw was this rather complicated and very exciting like of lots of features here. And that turned out to be not one, but two planets found in this system. And the system comprised a Jupiter-like object and a Saturn-like object. And they were orbiting around their lower mass host star, so a star which was lower in mass than our own sun, but they were orbiting around their host star in the same orbital ratio as Jupiter and Saturn orbits around our own sun. So we discovered this two-planet system which had their own Jupiter and Saturn. And this has interesting ramifications for people who are interested in figuring out whether or not it is necessary to have a Jupiter in a planetary system for the existence of habitable planets inwards of that massive object, and also whether or not, if you've got a large Jupiter-like object, if you also need to have a Saturn-like object to keep this large Jupiter object from disturbing the lower mass planets in their orbits over large timescales. So this is just a quick grab bag of the events that we're discovering with this technique. And we continue to make discoveries like this, both using data from the MOA telescope in New Zealand, plus also, as you can see, from data from other telescopes around the world, including our friends, the Polish US group, OGLE, and a host of follow-up telescopes around the world. I'd like to talk quickly about the evolution. So we're going from the survey observations through to now doing these observations from space. This is the Nancy Grace Roman telescope, formerly called the WFIRST telescope. As part of its mission, it will be looking for exoplanets using gravitational microlensing. This is the expected return of the WFIRST mission, and put into context with other discoveries found by other space telescopes, most notably Kepler. On the left here, we have a planet mass, and at the bottom we have the steady major axis in astronomical units away from the host star. The Kepler data there were known planets discovered using the Kepler Space Telescope. The blue here shows the expected discovery space of the WFIRST telescope, the Nancy Grace Roman telescope. What we find is WFIRST, or the Roman telescope, discovering Earth analogs, plus also planets right down to somewhat lower mass, including moons. And these moons are going to be icy objects because you will have noticed that microlensing tends to find planets which are cooler than ordinary planets orbiting in their habitable zone around their host stars. But interest is sparked regarding these objects as being potential homes for life because of the possible existence of liquid water subcrustal oceans. And so understanding how many of these sorts of objects are out there in the universe as well adds information to the people who are trying to nail down some of the parameters of the Drake equation, for instance. MOA collaboration is spawning another collaboration called PRIME. PRIME is an infrared microlensing experiment which will be building the infrared analog or sister of the optical telescope in New Zealand, the Michalski telescope. It will be placed at SAAO at South Africa, and it will be using top of the line infrared CCDs to make observations in the infrared. Why infrared? Well, the Roman telescope is an infrared telescope, and PRIME will be taking observations which are precursors or field selection observations to guide the WFIRST, the Roman telescope, in its observing program. Plus also, why infrared? Well, looking towards the galactic bulge is one of the prime regions for discovering exoplanets because there are so many stars in each field of view, and the chances of any one star being microlensed is very, very small. It's about 1 in a million. So you got to look at millions of stars. The center of the galaxy is obscured in optical light, but it is less obscured in infrared light, so there are more stars visible. And so looking towards this region, we expect to find about 12 planets per year using the prime telescope, and that will enable us to select the the best fields for WFIRST of Nancy Grace Roman to observe. So the MOA data will be used for WFIRST field selection, and one thing which I'm interested in looking at is you will have noticed that these observations here of that Jupiter-Saturn analog, where we found an extrasolar planet system which had a Jupiter and a Saturn-like planet, it was remarkably complicated. There were all sorts of bumps and wiggles, and as a data modeler, which is my research background, the fun is getting the wiggly line to go through the wiggly data. But even with just 2 planets, large planets, you can see that the bumps and wiggles are quite complicated. If WFIRST is going to be, since WFIRST, or Nancy Roman, is going to be so sensitive to lower mass planets, we're going to be discovering entire solar systems, and you get an idea of just how complicated the observed data are going to be. And so some of the work I'm going along with is trying to figure out how to best adapt existing algorithms to cope with that data analysis challenge. At the moment, 2 or 3 objects in a lensing system is okay, just doable. If we're looking at 4, 5, or 6, that gets very complicated very quickly. And so I need to have some more sophisticated algorithms to be able to cope with that data challenge. All right. I trust I didn't go over time too much.
Yeah, fantastic. And a wonderful slide structure. Yeah. Great. So you actually got a flurry of questions. We have time for a few. I think you kind of answered the first few actually in the second part of your talk. So I guess it's along the lines of statistically speaking, you know, how many exoplanets can you expect to find using microlensing, and how does that compare to, say, the transit mission using Kepler? Okay, that's interesting. Let's go to this plot here. So we tend to find fewer planets than transit being the transit technique. And however, the results that we get, you see, are complementary. The discovery spaces don't overlap completely. The transit technique, as used by Kepler, tends to find planets which are larger and orbiting closer to their host stars. Microlensing tends to find planets which are orbiting further away. So the mass function, or the number of lower mass planets in cool regions, is what microlensing tends to discover. And this is part of the motivation, because we're able to find these sorts of objects, and that mass function is something of particular interest to those of us who want to extend out the number of environments on which we might postulate life could evolve. Fantastic. And this plot also answers the next question, which is, you know, the minimum planet mass that can be detected. So the following question, and maybe the last one we have time for, is from Francesca Carey. So how many stars in our galaxy have rocky inner planets? Don't know the answer to that. Okay, then we'll do one more from Shrabani Patnaik. So would it be beneficial using microlensing to study our own Oort cloud? And yeah, this is an excellent question. And some work has been done in trying to figure out the so-called process of mesolensing or middle scale lensing, where we're looking specifically for objects which are much closer to us. I'm not an expert in that. But there are a number of people, particularly at Harvard CFA, who are interested in that. Yeah, so this is definitely a possibility. That's not my area of expertise, but yes, there are people thinking about using microlensing on much shorter scales, physical length scales, than galactic ones. Fantastic, thank you. Thank you so much, Nicholas, for presenting your great work, and we look forward to all that data getting analysed. So do we. I think you have a few more questions in chat, so I might direct you there. Yeah, thank you. So next up, we have Liton Majumdar. So if you would like to, please.
Can you hear me?
Yes, I can. So Dr. Majumdar, would you like to share your screen, please?
Yeah. Okay. Okay, so can you see my screen?
Yeah, it looks great. So please go ahead.
Okay, thank you. First of all, I would like to thank the organizer for allowing me to present our research work at this conference. A little bit about myself. Currently, I'm a faculty member at the National Institute of Science, Education and Research in India, an official visiting scientist at NASA Jet Propulsion Laboratory in Pasadena. After finishing my postdoc research at JPL, I took the opportunity to help my current institute to build the first dedicated center of planetary and exoplanetary science, where there will be a potential collaboration between the astrobiologists, astrochemists, astrophysicists, astronomers, and earth scientists. Today, I will present our recent work on glycine chemistry in space and its possible link to astrobiology. Okay. As you know already, hints of simplest amino acid, glycine, were found in samples returned to Earth in 2006 from comet Wild-2 by NASA's Stardust mission. However, possible terrestrial contamination of the dust samples made the analysis extremely difficult. But the Rosina mass spectrometer on the Rosetta spacecraft detected glycine along with related molecules like methylamine, ethylamine. Along with glycine and its related precursor molecules, you can see several families of other organic molecules, such as acids, alcohols, carbons, carbon chains, aromatic rings. They also have been detected on the Comet 67P. Then the obvious question is, what does the composition of Comet 67P tell us about how it formed? If we look at our human body, as you all know, 62% is water and 16% is proteins, right? Clearly, most of the oxygen and hydrogen is locked in water, and a significant fraction of carbon, nitrogen, hydrogen, and oxygen is locked in other various ingredients of proteins, right? Then the obvious question that we can ask, where is the glycine in space, or where are the precursor of glycine during formation of the planetary system? Why? Because the glycine is commonly found in proteins, and proteins contains a lot of fraction of carbon, hydrogen, oxygen, and nitrogen in our body. So if we really want to locate glycine in space and its precursors during the birth of stars and planets, we need to understand the formation of sun-like stars and the chemical complexity of the molecular glass involved during the formation of planetary system. As we all know, the space between stars is not empty, right? And it's commonly known as molecular cloud, where we know 99% is gas and 1% is coal dust grains. If we look at the first stage, where matter slowly accumulates toward the center of the molecular cloud, and central density increases while temperature decreases. As a result of this, atoms and molecules in the gas, they freeze out onto the cold surfaces of the dust grains, and they form icy grain mantles. In the second stage, when the collapse starts, the gravitational energy converted into radiation, and the envelope around the central object warms up, right? And the molecules frozen on the grain mantles acquire mobility, and they form new and more complex molecular species. When the temperature reaches out about 100 Kelvin, the icy mantle sublimates, and they give origin to the so-called hot core phase, which is very small in size. But this is the region where we expected to see various complex organic molecules related to the, related to life. Then with time, at the third stage, the envelope dissipates with time, and eventually only a circumstellar disk remains, which is also so-called protoplanetary disk. Now, in the hot regions close to the central forming star, the complex molecules are synthesized by reaction between the species formed in the second stage, as I mentioned. And in the cold region of the disk, which is basically the third stage, where the vast majority of the matter resides, or the so-called this midplane, the molecules that formed in the second stage, that is the photostellar stage, reach out onto the grain mantles again. And as a result, the dust grains then coagulate into larger planetesimals, the bricks of future planets, comets, and asteroids. So the dust grains that you see in the disk midplane or in the third stage are the the bricks for future planets, comets, and asteroids. So I hope I convinced you why glycine is important. But the problem is glycine is yet to be detected in any star and planetary forming regions. So what will be the strategy for the detection of glycine? So recently we published papers where we mentioned that where we worked on the chemistry of glycine, like how glycine can form in space, and then we tried to pick some of the precursors related to glycine. So that means what are the ingredients you need to form glycine in space, and that possibly can give you idea why you have seen glycine in different planetary bodies like Comet 67P and others. So what we did, we did a simple physical modeling, which is basically a static model where we try to model the formation of planetary system, which starts from a cloud and then it goes to the cold core state, then it forms the hot core state, and it gives eventually the birth of a solar-like star, what I mentioned in one of the slides. So this physical model eventually giving you the idea about the density, temperature, and other various parameters like how dust evolution is happening during the formation of planetary system. So this is basically your physical information that you need to model the physics of planetary systems, right? And then we coupled that physical model with a so-called thermochemical model where we included the state-of-the-art glycine chemistry using various laboratory data and also high-level quantum chemical simulation. And one such example is I mentioned here, like how you can see formation of glycine. Let's say you have a radical CH2 and NH2, it reacts, they form CH2 NH2, then CH2 NH2 reacts with CO, then it gives you CH2 NH2 CO. But obviously you can see the second stage has a huge barrier, like you need really high temperature of 7,000 Kelvin to form glycine through the third state. So the obvious point is whether you can have this amount of temperature when your star and planet is forming. The answer is no. So we really have to look for other chemical pathways by which we can form glycine even at the low temperature where it is expected to have function. So we find out three different set of reactions. First is reactions between methylamine, CH3NH2, and formic acid, which eventually gives you glycine on the surface of the interstellar dust grains. Then you have the reaction between NH2OH and CH3COH in the gas phase that can also give you glycine. And then you have four-body reactions that mentioned in part 3 that also can give you glycine. And also we have an ongoing effort at the JPL where we are trying to study ice chemistry of glycine on the surface of interstellar dust grains. So we are trying to compute various ice properties like the binding energy, how much is the energy or the binding energy of glycine when it sticks to the so-called dust grain. So what we found, the binding energy of glycine is very large, which is around 13,000 Kelvin. So that means when you form glycine on the surface of the dust grain, it stays there for a long time until you have sufficient temperature to dissolve glycine from the dust grains. So when we included all this information, like the binding energy coming from the planetary ice lab, the physical model that I mentioned, which includes the formation of planetary system, the chemistry that I mentioned in our model, when we do that, then we eventually can calculate the abundance of glycine in different phases. Different phase means abundance of glycine in the gas phase, abundance of glycine in the dust, and also abundance of glycine on the dust mantle. So what you can see here, this is the abundance plotted with respect to hydrogen atom, and this is basically the time scale. So the time scale is like we simulated until 1 million years, And the one striking thing is you can see the abundance of glycine is around 10 to the power minus 13 with respect to hydrogen, which is very, very low. And also glycine is mainly formed with the reaction CS2NH2 and COOH on the grain surface. But with the today's available instruments that we have, various telescopes, we can observe abundance until we can observe abundance up to 10 to the power minus 11, minus 12. So clearly, this abundance of glycine that we found is below the orders of detection. So that kind of gives us the possible explanation that why glycine is not detected yet in any star and planetary environments. So is there any hope to see glycine in the future? Before that, I should also mention the main chemical mechanism that is happening in our model to form glycine. So I mentioned you need CS3NH2 and HCOH to form glycine on the surface of the dust grains, because the reaction of the gas phase on the top, between NH2H and COH, it has a high activation barrier. So when if you want to form glycine on the surface, the CS3NH2, you have to remove one hydrogen atom from CS3NH2 to form CS2NH2, and then you can also remove one hydrogen from formic acid, and you can get COH. And this gives you the formation of glycine on the surface. But the problem is, as I mentioned, the binding energy of glycine, which is around 13,000 Kelvin. As a result, you will not able to dissolve glycine from the surface of the grains. And so it stays on the dust grains for a long time. So before it dissolves to the gas phase, it is basically destroyed by other radicals like CS3O and Na. And I should also add here, when Rosetta detected glycine, they also detected CS3NH2 together. So that gives you also a clue that why NH2CS2COH and CS3NH2 co-located on the observations of Rosetta. So any suggestion for new possible mechanism to form glycine, and is there any hope to see glycine in the future? So we are also conducted, we are trying to conduct one experiment at the Geology laboratory where we are trying to study the effect of superthermal hydrogen. So what is superthermal hydrogen? If you, let's assume you have a UV photons with the energy of 5 electron volt. And if you supply that energy to this reaction, CS3NH2, then 4.3 electron volt will be used for CH dissociation, and the rest of the energy will help to create excited state hydrogen atom or superthermal hydrogen. So you have enough energy in the system to overcome some of the barriers that you have in your reaction. So that means if you have a barrier in your reaction, which is 7,900 Kelvin, if you use superthermal hydrogen atom in your system, then your system will go through without barrier, and it will form the required molecules in a desirable amount of time. So in general, if you think about a reaction, let's say H plus CO2, which forms COOH, this reaction has a barrier of 7,900 Kelvin. But if you replace this reaction with excited state hydrogen, then you form
1 minute
COOH
remaining
without having barrier. Yeah.
Yeah,
so,
1 minute.
So when you have superthermal hydrogen in your system, we can clearly see in the plot here. So with superthermal hydrogen, we can reach up to an abundance of 10 to the power minus 7 for glycine. So that basically gives you idea whether glycine will be detected in the future. So the main outcome from our model is if we have if we found good source in star and planetary environments where there is a possibility to having superthermal hydrogen atom, then we can possibly detect glycine, which can give an example of origin of glycine in some of the planetary bodies. And recently, we also did observation using ALMA telescope. We found glycine precursors in many of the sources. And then I will summarize with this slide. So what is the future ahead? So as I mentioned, glycine is a large molecule, is a very complex molecule, and it has a large dipole moment and low partition function. And we also mentioned, I also mentioned that glycine has sufficient abundance when there will be presence of superthermal hydrogen. So if we assume there is a presence of superthermal hydrogen, and if we use that assumption, then what we can see, we can observe glycine using low frequency radio telescope, like in future, like NGPLA or square kilometer array, and we can sufficiently observe various lines of glycine in the future. And that can gives us hint towards observing life-bearing molecules in star and planet environments. Thank you.
Fantastic, thank you. So there are, we're just going to switch over to the next speaker while I ask one question. So thanks, Liton, for that great talk. And Aditya, if you could start sharing your screen, that would be great. Great, so we have a question. So if from Albert Fahrenbach, if your target molecule like glycine is adsorbed, is there any chance of detecting it spectroscopically? So just what, 2-sentence answer.
I think yes. So if glycine is, we don't have the idea of the absorption spectroscopy yet for glycine. And so if I understood well, if we really want to observe absorption spectra of glycine, then it has to be with ice. And we have, if we have the lines in the ice, then we can use James Webb Space Telescope in the future to look for the absorption signal of glycine. Yeah.
Fantastic, thank you. And I'll direct you to the chat for further questions.
Yeah.
Thank you so much.
Thank you.
Next up, we have Aditya Chopra telling us about Exo-Atmos, a scalable grid of hypothetical planetary atmospheres. So take it away.
Thanks, Anna. Can I just confirm you can see my screen?
Yes, and we can hear you great.
Great, thanks very much. Hi, everybody. It's great to chat to everyone, especially across the world in these pretty uncertain and weird times. I want to start on this figure that essentially in some ways tries to capture this journey of astrobiology, where we've gone from looking at astronomy to biologists and this journey of cosmic evolution. Today's talk is going to focus mostly on this region of this plot or figure, where we are looking at the gases that are involved in creating the habitability of planets. Earlier, someone was asking about how many planets are out there around stars that are rocky and in the habitable zone. And I think it's pretty safe to say that based on satellites like Kepler and many other sources of observing exoplanets, it looks like there are perhaps between 1 to 3 planets in the habitable zones of most of the stars we see in the night sky. And these numbers are probably around the order of magnitude similar for stars in any galaxy that we look at, like the Milky Way galaxy. What is interesting is over the last few years, almost a decade or so now, there's this emergence of studying habitability. And one of the main ways of doing that is to look at how far the planet is from the star and the type of star. And you might have seen figures like this that try and say, all right, if Earth is towards the middle of the habitable zone, what might be the limits of habitability if you consider Venus uninhabitable and Mars just on the edge of habitability. But even though this was the early approach at looking at habitability, it has since then evolved into a more complex version, rather than just considering a planet and how far it is from the star in this, what we would traditionally call the Goldilocks zone, where it's not too hot and not too cold. Because we have started to understand that things like plate tectonics, the composition of the Earth's atmosphere, the albedo of the planet, and a whole range of other factors like clouds and hazes, the magnetic field, are also involved in habitability. So here's a figure that tries to capture, from a review a couple of years ago, tries to capture the different factors involved in habitability. And you will notice that in most of these cases, so stellar effects, the planetary dynamics, the geological properties, a lot of these things are physics-based. And they are studied a lot in the community. And part of the reason is because if it's physics-based, you can create equations that can approximate the reality and run computer models on them. Whereas something more complex like the biology factor is a bit harder to do. Like any biologist will tell you, biology doesn't usually follow standard physics in ideal situations. And what we wanted to do in our work is try and address this missing link of biology. So the work I'm going to present today is mostly working in this area of the plot. And it starts with looking at the Earth itself as a starting point to understand the exoplanets' habitability in the universe. Now, if you look at the Earth, there's only a thin bioshell that is habitable. The terrestrial biosphere is not really the whole planet. It's a very thin, about 10 kilometer or so in size, if you look at the altitude, where life exists on our planet. And most of that is the atmosphere and the interface it creates with our oceans. And a little bit of it is also in the subsurface, especially in places where there's a lot of energy, for example, at hydrothermal vents. But we know that this bioshell has evolved over the last 4 billion years, both because of the action of the changing luminosity of our star, the sun, but also the evolution of the geology of our planet. That in fact is being mediated a lot by life as well. So as many of you will recognize, events like the great oxidation events, for example, in this plot here, about 2.7 billion years ago, and then again more recently, are things that happened when photosynthesis emerged, and then you had the land trees and land plants really increase the amount of oxygen put into the atmosphere. What we were interested in is, hey, if we were to look at the Earth's history and the changes in the atmospheric composition, would we be able to tell whether there was biology present or not? And in the longer term, if we were to look at an exoplanet with the next generation of telescopes, would we be able to distinguish just based on the atmospheric composition that we can detect remotely, would we be able to say whether there is life on the surface or not? And so we started that process by looking at the gases that are involved in biology and the abundances on Earth, and how they have changed over time. Here's a more zoomed in version of the previous plot that only covers the first 2 billion years or so of the planet's history. And you can see that early on we had a lot of CO2, which then dropped off very quickly. And then, you know, over here around 2 billion years ago, you start seeing the oxygen increase, and there's oscillations in methane and things like that as well. What was interesting to us is if you look at the gases that have evolved on in terms of Earth's atmospheric composition, they also happen to be molecules that are involved in some metabolic pathway in life. So things like water, hydrogen, carbon dioxide, methane, N2O. And all of these also have a greenhouse potential on the planet. Of course, we are all aware of the greenhouse potency of things like CO2 and methane, but the same is true for these other molecules as well. So could it be that life is actually mediating the composition of these gases in order to stabilize the planet? And you know, this would be an example of biological regulation of the habitability of Earth. Here's another figure that tries to capture the different gases that are produced because of life on Earth, and what the Earth's composition would look like without life. Of course, you see things like oxygen are missing, but even something like CO2, the abundances are quite different. So we are in the process of essentially creating a model where you can take what we understand about biology on Earth, simplify it, generalize it, look at specific gases that I just discussed, and then link it to the atmospheric dynamics of a planet like the Earth, but that can be more general as well. And our first step in that was to look at an off-the-shelf atmospheric model called Exo-Atmos. It's used heavily in the astrobiology community to understand the habitability of exoplanets. And we essentially parallelized this code. So this is a really old code built on Fortran 67, really hard to use, really resource incentive, but we were able to put it into what are known as black boxes or Docker containers, and then launch it on the Google Cloud, which meant we were able to do millions of runs of this code rather than just one or two on your local computer. And we created what we like to call a semi-automated search algorithm, where we told the computer where we wanted to end up, and it essentially planned a search strategy based on the resources available for it. So very simply, this code starts with modern day Earth, and then it perturbs the composition or the abundance of certain gases. In this case, on this plot, it's CO2, methane, and hydrogen and water. And then it kind of moves in a small incremental step away from today's present day Earth, and then produces a result, and then uses that as the launching point for the next set. And you can imagine over time, as it does more and more runs, it will actually expand out. And that's what you are seeing here. Over time, you can see as the code kind of moves in time, it is sampling more and more regions in this parameter space. Over here, it's 3 dimensions, but we did it in 5 different dimensions. But the idea is this code, because it's scalable and semi-automated, it could potentially, as long as you have the computing resources, keep going and sampling the entire parameter space. And so here are the preliminary results. This table kind of lists the gases we looked at and the increments we looked at. This is where we started, Earth, at about 15 degrees of temperature and 1 atmosphere pressure. And then we essentially generated about 124,000 different atmospheres. And we have now made this data set available through the NASA Exoplanet Archive. So if you're interested in looking into this a bit more, this whole data set is now publicly available, where you can download it. And essentially, you end up with the plots like this, where you can see the temperature and pressure profiles as a function of altitude. You can also get the surface fluxes of gases needed to maintain that atmosphere. So this data set is available, and in the future, this will go towards helping studies using telescopes like GMT, the James Webb, and the next generation ones like HABEX and LUVA, to make sense of the observations that we get. So chances are we won't be seeing planets like this or images like this anytime soon, but what we will be seeing are these sort of spectra. And part of interpreting these spectra is that you need the pressure temperature profile and the atmospheric compositions to input into your model to compare to your observed spectra, so you can figure out what the abundances are and what the disequilibrium looks like in the atmosphere. And what we have essentially done is produced 124,000, but hopefully even more in the coming months, that will become the input for these kind of studies.
1 minute left.
Thank you. And on the biology side, what I'm working on is looking at, now that we know what surface fluxes are needed to maintain each of these atmospheres, can we look at the Earth's history and the history of the phylogeny of life on Earth, and what metabolisms arose where, to essentially say, could biology have maintained those fluxes or be compatible with those surface fluxes of gases that we see in our atmosphere, to tell us more about what kind of biology might be present on other planets. I'll leave this as the summary slide. This is kind of what we have done so far, is looked at only the composition, but in the future, our code should allow us to look at different types of planets and stars. And we're also looking at making use of machine learning to essentially make our code and strategy a bit more resource efficient. I'd like to thank the NASA Frontier Development Program, which essentially helped kickstart this program and now is part of my postdoc in the Netherlands. Thank you.
Fantastic. Thank you so much. Beautiful slides and wonderful work linking the history of life on Earth with atmospheric chemistry. super fascinating. So because of time constraints, I'm going to ask you to please answer the questions in chat. And
Sure.
I'm going to ask our next speaker, which is our first invited speaker of the conference, Dr. Joe Michalski, to please share his screen instead. So thank you, Aditya.
All right, so just for a moment, getting in here. So I hope, can you see my screen now?
Not yet. Sometimes it takes a moment or two for it to load.
Okay. All right. I hope that is working.
I don't see it yet. If others can see it, please, let us know in the chat.
Okay. So I'm on, yeah, share to everyone. There you go. Oh, this should fix it. Sorry about that.
Yeah, it's probably a security setting, huh?
Yeah, I apologize.
Oh, no problem. So while you get that set up, I'm going to tell everyone about who you are. So super excited to have our first invited talk to end the first session of our first day. More to happen in the afternoon. So Dr. Joe Michalski is a geologist and planetary scientist, interested in mineral exploration and the relationship between geology, mineralogy, and life. So he's an expert at using remote sensing to study the mineralogy and geology of planets. So that kind of ties into the previous talk, maybe. He also uses laboratory and field research to investigate mineralogy and geomorphology of deposits that are formed in hydrothermal, volcanic, and sedimentary environments on Earth to better understand the processes that operate throughout the whole solar system. So it's a whole variety of different environments. He's currently at the University of Hong Kong, where he's the acting director of the Division of Earth and Planetary Science, the assistant dean for knowledge exchange, and the deputy director of the Laboratory for Space Research. So very, very busy academic. He's also involved in mission planning and landing site selection for future missions to Mars, to our moon, and other solar system objects. And before joining the University of Hong Kong, he was a research leader at the Natural History Museum in London, a senior researcher at the Planetary Institute, and also researcher at JPL and the Institute of Astrophysics, I can't pronounce it, the Paris Institute d'Astrophysique Spatiale. He carried out his graduate studies at Arizona State University. So without further ado, I'm going to let Joe tell us all about his exciting work. Thank you.
Okay, great. So on my side, I see a green light that says you are screen sharing, and I hope that that works.
It looks beautiful. Thank you.
Oh, okay, good. Great. Okay. Well, thank you very much for the invitation to speak and going through such great effort to bring people together. Even though everybody is challenged by these unusual circumstances, it's still totally worthwhile to do and exciting for all of us to connect in that way. So thank you. I just want to acknowledge before we start that finally, after a few years at Hong Kong, I've sort of built up my team to be, I think it sort of does take 3 or 4 years to kind of get everybody rolling, and we're doing that now. So I want to acknowledge our funding sources and the different labs that we work with here. And just to mention that this is a group effort, so I'm presenting on behalf of some members of my team who are all really awesome students. And so shall begin there. Okay, so most of the time when we talk about Mars, what do we talk about? I guess it really comes down to wanting to understand climate. Climate is obviously linked to habitability in a lot of ways. And we understand that through characterizing geologic processes. And so in this talk, I will be speaking with you about various geological processes and about climate. So this is a little bit of a grand tour. So forgive me if I cover a few too many things. And I'm not very excited about this. PowerPoint does this autosave and downsample things, and some of the images look bad. But anyway, sorry for that. Okay, so we're going to talk about volcanism, because volcanism is one of the main ways that we produce the atmosphere on Mars. And of course, there's some discussion about delivery from comets and things like that, but volcanism would be the main way. And also it creates, as you'll see, sedimentary rocks and affects surface processes there. So I'll speak to you about those things. And then we'll look at some global scale weathering patterns that we've seen in the last 10 years or so, and chat a little bit about greenhouse gases and what that might mean for lake and marine environments that would be of interest. And also I want to mention that I've got a bit of a sore throat, and if my voice just goes out, then there's nothing I can do about that. Okay, so volcanism on Mars is an exciting topic. Mars has long been recognized to be a volcanic planet. Since the first exploration of the planet, we've seen what are literally the largest volcanoes in the solar system, really striking morphologies, long lava flows, beautiful shield volcanoes. And generally speaking, our view of volcanism on Mars has been shaped mostly by evidence for these really big shields, because they're well preserved, they're beautiful to look at, they're well defined, and so they're easy to map. Although it does take a lot of detailed mapping, I don't mean to say it's easy in that way, but it's kind of straightforward because you see lava flows, you see boundaries between units and can map them in a straightforward way. Now, that's not to say there's never been any discussion of explosive volcanism on Mars, but in fact, it's been sort of under discussed. There are a few shield-like stratovolcanoes that have been discussed over the years, but generally speaking, it's a little bit confusing to look at the history of volcanism on Mars because theory predicts that all volcanism should be much more explosive on Mars in the lower gravity environment than it would be on Earth, all else being equal. So what does that mean? It means you don't necessarily need very wet magmas. You don't need silicic magma evolution in order to have explosive volcanism. And that's mostly just because the lower pressures in the crust result in bubble nucleation and basically explosion of the magmas. And a lot of that work has been described by Lionel Wilson and his team from the UK. So when we think about volcanism through time, one of the issues is that we can look at theory pointing backwards from about 1 or 2 billion years ago to 3 and 4 billion years ago. And modeled predictions of heat flow show a certain amount of volcanism through time. But if you look at the same sort of problem through the lens of mapped lava flows and do various corrections and calibrations to interpret extrusion or eruption of gases, you can sort of try to match the volcanic mapping with the model prediction, and they follow more or less the same pattern, even though they're offset by an order of magnitude, until you get to about 3.5 billion years ago. And there's a big disconnect then. So why is that? Well, the obvious reason might be that there was just a lot of erosion. And so that record has been lost, has been destroyed on Mars. But in fact, we do have a lot of units that are older than that. And so one possibility is that we've misunderstood some of the key evidence for volcanism early on. And that's what, along with some colleagues, along with my colleague Jake Bleacher, I proposed a few years back now in a Nature paper about explosive volcanism in Arabia Terra. And the idea here was basically that we saw some evidence for really big calderas that are between 70 and 100 kilometers across, for example, that are basically not constructive features. They don't have, they don't form mountains, they don't form shields, and they don't produce long lava flows. They just blow themselves up. And so, but they're clearly not impact craters, and they are associated with some friable ash deposits and so on. So we proposed that these were actually a new category of caldera on Mars, and understanding them better would be really important for having a better calibration of what type of volcanism occurred on early Mars and understanding how that has affected the planet's history. So actually, I just got a student now named Yo-Yo Chu who's working on this, and so she's going to go back and reevaluate evidence for calderas on ancient Mars. And if you think about it in terms of volcanism on Earth, I mean, I know that the word supervolcano is not necessarily one that all geologists love, but it does communicate something pretty directly. It communicates that the process was extremely explosive, basically blew itself up and is structurally complex. And those are the main things that we're trying to communicate with this work, is that we think Mars had a number of those kinds of features and would have produced huge amounts of ash, even mafic and ultramafic ash, that would be, of course, quite reactive chemically to any surface water and so on, and also would have produced volcanic gases that would have impacted climate. So even on Earth, these features can be a little bit difficult to interpret because they're so destructive, which is why we didn't know a huge amount about them until relatively recently. But it appears this is something that might be commonplace on Mars. Okay, this is not work from our group, but something I want to mention. Sedimentary rocks get a lot of attention on Mars, and they should, because they're interesting. As we try as a community to understand the climate history of Mars and the implications for astrobiology, we really focus on sedimentary rocks, and we enlist the expertise of some of the best known and most competent sedimentary geologists on the planet. And but as we compare what we see even on Proterozoic Earth, we might be a little bit off base with regard to the nature of most sedimentary rocks on Mars. And what I mean by that is where we've looked at them in up close and in detail, it appears that sedimentary rocks on Mars mostly seem to be made of poorly crystalline materials, along with some feldspars and pyroxene and olivine, and basically they look like volcaniclastic type materials. So immature sedimentary rocks that have not experienced long-lasting sort of basin evolution and things like that. Mostly airfall deposits with a lot of glass in them. Of course, impacts can produce some similar types of materials as well. And process-wise, in terms of reactivity and geochemistry and stuff, in some ways, the distinction between those two wouldn't matter in certain cases. But here's an example from Gale Crater, where the Rover team has shown that you have tridymite present within the ash deposits there. So it's a pretty smoking gun kind of piece of evidence that those rocks, at least some of them, do have a volcaniclastic origin, and this might be a fairly common thing on Mars. When we've looked at them at Meridiani and Gusev Crater, we see other evidence like that basically says we see rocks that are chemically similar to basalt and komatiite that have added sulfur, but they may have textures that could look sedimentary. Why does it matter? Well, because I want to talk about weathering sequences and global scale alteration. And basically, for me, I believe it's a big part of the story that the rocks that have been impacted by this type of weathering are probably volcaniclastic. And that means very susceptible to weathering, which means they may not have had to experience very long climate excursions in order to produce clay minerals and things like that. This is a landmark paper in 2015, in my opinion, by John Carter and a French team. They are the ones who developed the Omega instrument and flew it to Mars aboard the ESA Mars Express spacecraft. And this paper by John is interesting because he shows many, many examples of aluminium clays that are overlying iron and magnesium clays on Mars. So in case you're unaware, most of the crust of Mars is almost entirely basaltic based on gamma ray data and mineralogical data from other instruments. So within that mafic crust, we get aluminium clays, which means there's been some chemical segregation and some would say leaching, that we have to be cautious about how we use that term, I believe. So this is a really interesting paper, and I've got a student now, Bin Long, who's working on this topic and trying to look in more detail at all these different exposures of weathering sequences. The idea is really to try to understand whether you see only one evolution of these weathering sequence. Like, in other words, do you only have aluminium over iron in certain over iron magnesium clays in one sequence, which you see, and you see that sequence everywhere, or do you see repeated patterns of aluminium over iron magnesium, and then another package on top of that, aluminium over iron magnesium, and so on and so on. And so because that would mean that you had some punctuated climate excursion, and then you had more volcanism, and then another climate excursion, then more volcanism, another climate excursion. And I really thought that's what we would find, but Binlong has shown through some thorough work looking at the whole surface that we don't really see much of that. It seems like there's only one, there's never a repeated section, or almost never. And we're trying to make sense of that at the moment. So when we talk about aluminum clays over iron magnesium clays, what you basically see are these kind of rock sequences like in the image in the bottom left. I'll talk to you more about those now. So in Binlong's work, he's looked at some interesting cases where on volcanoes themselves, which are perched up above the surrounding plains, there are pretty clear cases of this weathering sequence of kaolinite and other aluminium clays and elephane. Elephane is a poorly crystalline, you could maybe call it a protoclay, a short range order phyllosilicate, fairly common in volcanic soils. And we see that in this kind of, in volcanic settings on Mars. So he's mapped them out in cases where they're very clearly present in what would be ash deposits. So that doesn't mean that all of them are formed the same way, but it could mean that many of them are, because he sees it in many cases. Here's an example of what those kind of results look like throughout the surface. So in pink and black dots, you have volcanic source regions. And I'm sorry, so pink units and black dots. And then in the pink stars, you have the weathering sequences. And he's able to connect those spatially through mapping. And in his opinion, we are seeing some pretty clear examples that there's quite a lot of weathered ash on Mars. Okay, so now I want to tell you about something that's really cool. One of the striking things about Mars is that when we look all around the planet, we see this blue unit overlying like a yellowish unit. So in other words, I mentioned to you that there's this weathering sequence of aluminium over iron magnesium, but actually when you look at so if you look at those in terms of infrared data, you can actually detect the aluminium clays and the iron magnesium clays and so on, because you're looking at vibrational features of the minerals. But if you look at visible light data, in other words, high resolution images, like we're showing here, you actually see a bluish toned package over a yellowish toned package. So this is obviously telling us something important, and perhaps something different than what the infrared story tells us. I realize these plots are a little bit busy. I'm just kind of pointing out that, so these are all results from another student named Zhaocheng Liu. He's working on laboratory spectroscopy to help interpret the things that we see in Mars remote sensing data. And in fact, that's one of the main objectives of the PSML lab we have here at Hong Kong U, is to support missions and interpret data better and so on. So these plots just show blueness and brightness of the materials. As you would be probably aware, iron 3 rich rocks will be pretty red most of the time, and iron 2 rich rocks can be fairly dark most of the time. And by looking at blueness and brightness, we can distinguish between various forms of iron, and that's based on lab data that he's plotted up here. And we can apply that to actual indices that we can apply at Mars and really map out iron content. So here's an example of a long drill core that was drilled through, well, I guess about 55 meters of weathered basalt in Hainan Island. And Hainan Island, if you don't know, it's part of China. It is it's very near Vietnam, so in the southwest of China. And it's a tropical environment with intense weathering. So there certainly would be elements of that are not perfectly analogous to what we see at Mars. But, you know, a lot of the science we do is focused on availability and what we can work on at any given time. And this drill core still allows us to look at weathering intensity, element mobility, and spectral indices, and so on. So there's an important difference, which we'll discuss soon. So this is an example of some of his work where he's able to take the spectral indices that show hydroxylation and hydration of the rocks, element mobility over a scale of tens of meters, and compare that to comparably weathered sections on Mars. And it gives us more confidence that we understand what's happening in the weathered sequences. But there's one really important difference. It's quite cool. I think the most important part of his work is that he's able to show that iron does not follow aluminium in those sections. So iron is quite immobile under oxidizing conditions, but quite mobile under reduced conditions. And so we believe that this blue horizon and the spectral indices that we're able to use to map element mobility, we believe that those show a decoupling of iron and aluminium. And that's really important because it means that these things were probably weathered under a reduced atmosphere. And to my knowledge, this is the first time that we can show that with geological evidence for Mars. There have been a number of models that suggest it, but I'll come back to that in a moment. And this trend is comparable to what we see in some Archean paleosols on Earth before the GOE. So in Jiaoqing's model, effectively you have volcanic outgassing, production of volatiles that react with the surface units. That could be shattered regolith from meteor impact, but also volcanic ash and various other lavas. And it results in a downward migration of the mobile cations and produces these blue horizons that we see around the planet. So it's important to us because we've known since the 70s with Jim Casting's work and Sagan's work that a CO2 greenhouse doesn't really work for Mars. You have the faint young sun paradox, and you get some other feedback mechanisms by if you have too much CO2, you can produce too many clouds and you cannot really warm the surface dramatically, which has led modeling type folks to conclude that you need a significant fraction of reduced gases in the atmosphere. And here are just two of those papers, but two very interesting ones to have a look at. And we believe that we see the geological evidence to support those. So that's quite cool. Okay, so now I'm going to try to end within about 5 or 10 minutes so that we can have plenty of time for discussion. But I want to speak a little bit about the idea of what does this all mean for habitability? Well, I guess sometimes Mars gets oversold in its habitability, in my view, because we can find extremophiles present in many different environments on Earth. But extremophiles, they maybe could hang on or exist in many environments on Mars, but does that really mean that the environments that we're looking for were ideal for development of complex chemistry, like in terms of initial development? And so I hope that will make more sense as I move on. So we see channels on Mars and various types, and we see mineralogy indicative of aqueous processes that occurred in warmer atmospheres. But generally speaking, ancient Mars might have been relatively cold, quite arid, and certainly quite radiated. So this diagram shows the Noachian crust of Mars in brighter gray, light gray, and it shows various lakes from based on data from Facet and Head. And what you can see here is that most of the lakes are relatively small, and that means not very voluminous. And we can estimate how big that lake would it be based on altimetry data today. So that means that even though the lake has been dry for a long time, we can use the laser altimetry to see where is the base level and how does that relate to the topography of the basin, and calculate how many cubic kilometers of water must have filled it at any given time. And those are minimum estimates and so on. But generally speaking, most of the lakes are relatively smaller and a few of them are quite big. So why does that matter? Well, if you had okay, so we have many different types of lakes on Mars. Some are small, some are large, some are very ancient, some are less ancient, shallow or deep, some dominated by surface flow, some that would have been supported by primarily groundwater. Some would have been quite acidic, and we can see that in terms of the mineralogy that's preserved there today. Some would have been alkaline, and many would have been short-lived. Even the deltas that people talk about, and even the eroded channels that people show in their talks, these things can have formed in tens of thousands of years pretty easily. So if you think about it, say you had a extremely arid surface that was radiated and cold, but then you have a short-term climate excursion, all that reactive glassy material that is potentially mafic or ultramafic in composition would be susceptible to alteration relatively easily and would be mobilized relatively easily. Anyone who's been in a desert storm knows that you can reshape the landscape even in a weekend pretty easily. So the question for Mars then is what does this geomorphological and mineralogical record tell us about long-term habitability? So lakes are very interesting and we love them, but they're not all equal. And I'm also worried a bit about radiation. And I would like to collaborate with somebody who's able to model radiation at the Martian surface. So if that happens to be you and you're interested, please contact me. Basically, we want to be able to understand the flux of galactic cosmic rays, solar energetic particles like solar wind and UV, and how those different fluxes would be attenuated by various amounts of ice cover or various thicknesses of water in a lake, and also in terms of the penetration to regolith itself. So that's a little bit more straightforward. So if you had a lake environment, so we sort of assume that we want to have a photic zone where potentially photosynthesis could take off, but in fact, it would be quite a dangerous environment for organisms and maybe not the best place for certain types of complex molecules to form. So we have to, with this in mind, we might think about which kinds of lakes would be the most interesting for astrobiology. And I think the ones that are quite deep and voluminous, ones that are linked with hydrothermal systems, ones that have clear evidence for chemical energy sources, and those that even contain evidence that there were sharp chemical gradients in them, those to me are the ones that are most interesting in terms of habitability and abiogenesis. One of those is the Eridania Basin. Now, I do realize that not everybody thinks that the seafloor on Earth was necessarily the cradle of life. And there are a bunch of reasons to think that, and some reasons to not think it as well. But nonetheless, it's an interesting geochemical environment. I think we can all agree. So in this particular part of Mars, we have what I believe are genuine seafloor type deposits. So this was originally mentioned as a likely massive series of lakes. And actually the geomorphological evidence for that is quite strong. So we went back and revisited this and looked at the actual volumes of water involved. I mean, the volume of water here in this particular basin would have been equivalent to all the other Martian lakes combined. So quite a lot. And why does that matter? Well, just in terms of longevity and duration. So then when you look mineralogically at the materials in here, you have to untangle a few geological mysteries, but basically it comes down to this. You had a lot of volcanic resurfacing, you can see, at the top. And then the oldest bits of the basin are poking up sort of like kapukas, but they're just altered basin materials. And so by looking at those, we actually see some really interesting deposits from the deep ancient basin floor. And so what we do in my lab then is we look at the clay mineralogy and characterize the structural and geochemical substitutions in the clays and try to relate that to what we see on Mars. And in this case, we can show many different types of iron-rich clays present in that environment. In addition, so you have, the legend here doesn't show all of the right material in the bottom right. Sorry about that. But basically, this is a topographic map of Mars, of the Eridania area, and then the darker blues are deeper in the basin, and the lighter blues are shallower. So that tells you how deep the water would have been. And something that's quite interesting is that look at the yellow dots for a moment. I don't know if you can see my mouse, but moving around the edge of the basin, you actually see that the yellow bits are all occur in the coastal areas. Well, those correspond to salts. And the green bits and the orange bits all correspond to what we interpret as hydrothermal clays deep in the basin. So this is the kind of setting that would have been really interesting about 4 billion years ago on Mars and could have been protected away from short-term climate excursions, could have been protected away from harsh radiation, and could have had a lot of chemical energy sources to potentially lead to abiogenesis. This is the image on the left, shows you a false color image of the actual rocks themselves. So those things were described in a paper that came out a couple of years ago. And also for, I guess everybody here is the astrobiology type. If you might take an interest in this other one, a perspective paper that we wrote in Nature Geoscience that addresses the question of how we can use Mars as a window into the origin of life here. And more or less concludes that we really ought to be looking at hydrothermal systems more than just lacustrine systems, long story short. So I think that is about it. Yes. There's my lab. Send me your good students, please. And that's all.
Hey, fantastic. Thank you so much, Joe. Those definitely had the flavor of a grand tour. I think that's really great for this audience. So we've amassed some questions during your talk. So we'll go through those first. And then if you had any sort of controversial things you wanted to lead a discussion with, then I'll let you take back control again. So first of all, we have a question from Shravani Patnaik. So why does the Tharsis Plateau contain a significantly large number of volcanoes? And is it analogous to our Pacific Ring of Fire?
Yeah, there are some analogous aspects in the sense that Mars is considered by most to have been a one-plate planet. And I realize it can be a little bit controversial to people. Nobody really knows the answer of exactly when plate tectonics started on Earth. But I think most people think it's between 2 and 3 billion. But by that time, Mars had already kind of geologically kind of cooled the jets a little bit. So in that area, anyway, it's one big thick plate that had mantle plumes that have built up really large shield volcanoes in that area. So it is similar in that way.
Okay, super fascinating. Great, so the next question is from Francesca Carey. So I think you've partly answered this already, but if there's anything else you want to add, now's the chance. Are clays on Mars generally formed by weathering, or do they form in an aqueous environment? I guess you showed us maps and kind of answered that, but if there's anything else you wanted to add, please go ahead.
Well, Yeah, there's been really quite a lot of excellent work over the last really 15 years using infrared data to detect and interpret clays on Mars. Actually, there are quite a lot that are exhumed from within the crust by meteor impact or deep erosion. And those are clays that many of us refer to as crustal clays or subsurface clays. And actually, in looking at those environments in detail, we can start to reconstruct what the subsurface environment of Mars might have been like. And there's a whole group of us who feel that the Martian subsurface would have been a really interesting aspect of its habitability and even potentially interesting for abiogenesis. So in other words, a deep biosphere on Mars. Now on Earth, the deep biosphere is quite sparse, and there are all kinds of reasons to be concerned about that on Mars. But it seems that a lot of the clays formed in that environment through hydrothermal processes. But also there are many that formed in layered rocks at the surface, and those appear to have formed by top-down weathering. So I think that's the answer.
Okay, thank you for that. Okay, so next question from Harold Bernhardt. So is there any evidence for mixed hydroxide, such as green rust or hydrotalcite on Mars?
I've certainly looked for both of those things in a couple of environments, and there's no convincing evidence for either of those at the moment. But it's something that's on our infrared radar, so to speak. And they can be hard to detect because they can be quite metastable. And so a few billion years of oxidation and erosion can destroy some of those materials. So no, we don't have them. We haven't found them yet.
I see. A bit of a battle. Okay, so next question is from Akanksha Mahapatra. So firstly, they wholeheartedly agree with you about Martian habitability being overestimating for Earth-like life. And then the question is, wouldn't Jovian moons hold more potential for preservation of biomolecules?
Yeah, I guess I don't like to engage in the either or scenario. I understand why we do and why we must, and there are sort of limited resources that get allocated to different groups and different missions. But I guess I say we explore all of them because it's hugely interesting no matter what. The one difference I would say is that going to basically any of the icy moons would probably inform quite a lot about prebiotic chemistry. But going specifically to Mars informs us about the processes that occurred at the same time when life formed on Earth. So in a similar environment at the same time in a parallel planet. Whereas the conclusions we would make from studying icy moons are clearly super interesting, but may not have the obvious overtones for Earth.
Oh, fantastic. Yeah, so there's a great reason to explore everything. Yes. Next question from Michael Rowe. So firstly, fascinated by the decoupling of iron and aluminium enrichment zones. And then the question is, what chemical processes / mineralogy allows you to generate iron enrichment if it is mobilized as iron 2? Are you looking at a subsurface oxidation front?
Yes. So it appears that these the leaching zones are something like tens of meters thick, which is still quite a lot. I mean, I was surprised by that. But what exactly causes the oxidation zone is part of the mystery yet, but we are definitely thinking about that.
Okay, great. Next question is from Martin van Kranendonk. So given the strong evidence for glaciation and cold conditions, how many of the river or lake features could be subglacial? And do we know?
Yeah, so thanks for that question, Martin, because I think there's a little bit of there's an opportunity for a lot of discovery level science in terms of glacial geology on Mars. The reason I think that is because we've dismissed a lot of the evidence for glacial activity on Mars over the years, partially because we don't see very many things like eskers and boulder bars and braided streams and those sorts of things and moraines. But that may be because glaciers on Mars are largely cold-based, and it might be that a lot of the sediments are fine-grained ash, and so they just simply don't produce. You're not eroding quartzites out of the Canadian Shield, so you don't make the same kinds of sedimentary materials with glaciers that you would on Earth. But that being said, I think there's a lot of evidence that there's been ice-related activity, and in fact, even the ash deposits themselves could be so porous that it actually could diffuse a lot of ice into the rocks and make rock glaciers of sorts. And there's just quite a lot we don't know about all that. And also in terms of ice-mediated geochemistry, some of my colleagues have shown that within the ice, you can make hyperacidic solutions that can dramatically alter the mineralogy, but it's still a chemically closed system. So all those things are hugely interesting for Mars, and I think there's quite a lot we still don't know about the glacial environment there.
Yeah, fantastic. It's amazing also what you can gauge from high resolution images. Yeah, so I guess I had a question about, question from Maggie Lau, a few short questions. Maggie, if you have a few short questions, do you want to just unmute yourself and then you can have a back and forth instead?
Sure. Hi, Joe. First
Hi,
time. Oh, great. So I have, I'm interested in also the rocks, the basalt bedrocks in Hainan. Just curious, how did you first find out that they exist? I mean, the blue band exists in those bedrock in Hainan. And then also with the explanation that the iron may be leaching out, leaving the aluminum enriched, what is the hypothesis behind that the rocks is on the surface exposing to air instead of being submerged underwater?
Okay, let me see if I understood those things. So first of all, the Hainan rocks, actually that drill core was funded and carried out by the Guangzhou group led by Professor He Hongping. I'm sure you know him. I don't, and the application of all that stuff to Mars ended up being kind of a secondary thing. So we don't actually see as like the blue horizon in those rocks. We just see, we are able to develop spectral indices that quantify hydroxylation. So we get a whole series of hydration processes and then a whole series of hydroxylation processes where it actually dissolves out mobile cations with water complexes and breaks down the clays and ultimately breaks them down into hydroxides. So there's a lot we can learn from that process, but we don't, but the specific blue horizon isn't one of them in that case. But if you want to explore that more, you can contact Jiaoqing directly or email me and we'll discuss. And then in terms of the blue horizons on Mars, I believe the question was, why do we think that was subaerial and not subaqueous? Is that correct?
Yes.
Okay. Yeah, so that's where some of the global scale mapping from another student named Bin Long, he's been looking at the topographic context of where those horizons occur. And we see them as draping units at elevation above the surrounding plains. So it appears that the context is inconsistent with water in a basin in those cases.
Thank you.
Thanks for that. I guess I'll ask my questions. The first one is you mentioned dust storms, and our previous speaker mentioned wind as a pretty important factor for habitability. So I don't have a good sense of the like what the wind is like on Mars. Like how is it very similar to Earth? Like the atmosphere is kind of different. So yeah, what happens there?
Well, so first of all, I'm the kind of scientist who can watch a film like The Martian and enjoy it, because it doesn't have to be perfectly correct all the time to to be an interesting film. And there are, in that film, if you've seen it, the wind does blow like small cobble-sized pieces and large gravel-sized pieces of stuff around. So that's not what's going on. The wind velocities on Mars can be really, really high, but the density of the atmosphere is really low. But it turns out that the particles that are mobilized on Mars are about the same as you get on Earth. So you get if I'm recalling correctly, you get a peak grain size in most of the aeolian deposits or in dunes, peak grain size of about 100 microns or so, 100 to 300, something like that. And then, but there are huge, huge deposits of less on Mars. And it's another element of Mars geology that's just not very well explored. There are about 5 PhDs in Martian list deposits, I believe.
Okay, yeah, thanks for that. Yeah, I would not have noticed that in the Martian at all. So I guess my other question was to do with, you know, when people look at impact craters, like how much access do you get to the depth? Like of the stuff that gets kicked up, like.
So a good rule of thumb for impact craters is that they exhume. So people who are experts in impact geology are pretty particular about language, and because words have very specific meaning. So an impact crater will, generally speaking, can exhume materials from about 1/10 of the final crater diameter. So when the crater occurs, there's something called a transient crater diameter, and then that kind of fills in and relaxes. But to make life simple for us as geologists, thankfully, if you see a 30-kilometer impact crater on Mars, the central peak materials would represent things that are approximately 3 kilometers depth. That's an average of a lot of different data, you know, so in any certain circumstance, it's probably not true for that particular one, but it's roughly speaking true. But the other thing that's important to mention is that people sometimes think that when an impact crater occurs, that the whole substrate gets intensely shocked, and that's not true. The shock waves propagate like a head of cauliflower or something like that in 3 dimensions. So there are intersections of the various waves that get localized, and you can get intense mineralization at that scale. But so if you're in the field, you might be standing on something that's quite shocked and then walk 2 meters away and not be. Or even in a hand sample or in a microscope, you can look at things that are. So I did some shock experiments with clay minerals, and what we found is that for something like kaolinite, there's not just a linear shocking from like something that's unshocked to something that is quite very shocked and melted. Actually, the thing that's linear about it is that you get little areas of the clay that are totally shocked, and as you increase the shock pressure, you just get more and more of those little areas, and you only really see that in TEM. It's sort of weird, but interesting.
Yeah, I guess it's something important to keep in mind. If you can't map it in high resolution, then yeah, it's good to know like that there are those finer features there. So we have another question from Harold Bernhardt. So apologies if you mentioned this before, but are there any of the target sites of the current Mars missions ancient or deep lakes with evidence of hydrothermal activity?
It's a sensitive subject, I think, for people, landing site selection. So the Gale crater site has been geologically an absolute wonderland, but it wasn't chosen for that reason. the Gale Crater site where Curiosity rover has been for the last 8 years or so, that contains pretty clear evidence for transient lacustrine conditions, but not really the kind of, the reason I say it's a little bit sensitive is that you can actually see some redox trends in manganese. There's a really cool paper about that by Nina Lanza. And there are some other pieces of evidence where you think maybe there was some lake bottom redox chemistry that was quite cool. But generally speaking, that site wasn't chosen for that reason. The upcoming ESA mission will not go to a site like that. It will land in the plains and look at ancient terrains. That'll teach us quite a lot about Mars anyway. The upcoming Chinese mission is, the landing site is chosen specifically to avoid challenging situations because it's more like an engineering, the landing site selection was driven by engineering concerns. So that will be looking at more like flat terrain. And then the upcoming NASA mission that recently launched will go to Jezero Crater, which was largely chosen because of the delta environment, which will have a lot of cool sediments. And I mean, I guess once you get your boots on the ground and you start popping around anywhere on Mars, I think you're going to find cool stuff no matter what. So again, that site wasn't chosen because it's thought of as being a hydrothermal lake. But if you have an impact crater, you have heat flow, and you would probably have, because you would deposit heat into that crater, and then there would, I'm sure that we'll find some kind of evidence for hydrothermal systems at some point.
Yeah, thank you for that answer. And if there are any, if there's anyone else who wants to unmute themselves and comment on that topic, like Martin or Mitch, for instance, then feel free to do so. We have a few minutes left for some discussion before we let Joe go. Yeah, so Joe, is there anything you wanted to posit to this audience and get some feedback on, or?
Well, I'm curious about whether people think this matters, this issue about radiation environment on early Mars. I'm showing a slide right now. And I've always just thought, you know, if you had a transient lake that only lasted, 10 or 100,000 years, and it was, the magnetic field shut off of Mars at about 4.1 billion. So if you want to crank up the energy on a lake, and for 100,000 years, but it's being bathed in radiation, such as cosmic rays and solar wind, do you think that is a problem in terms of prebiotic chemistry?
Yeah, so I guess the question is it a problem, or does it actually help some chemical reactions come along? I guess not in the context of Mars, but Dimitar Sasolov and Zoe Todd and some others have been working on looking at sort of shorter wavelength UV and how that impacts particular reactions, and how the exact wavelength actually matters for certain reactions. So I know some people are looking into it experimentally, and Albert Fahrenbach, who is an academic at UNSW Sydney in chemistry, he's a prebiotic chemist, and he looks at gamma rays. So yeah, a few prebiotic chemists around thinking about this. I think there are also some atmospheric chemists who actually try to figure out the flux of all of these on the surface of Earth, and those models can translate to Mars. So I'll try to get some names to you just to see if people can do some quick calculations. But for anyone else present here, if you have thoughts or comments that you want to add to this, please let me know.
And this is the main reason that the ExoMars rover has a drill on it that is theoretically capable of going to 2 meters depth. It was because of some couple of papers that modeled the flux of radiation at the Martian surface and showed that by about 2 meters deep, you would be out of the danger zone. But
I see. Oh, from
it's
these
quite
high
hard.
energy sources.
Yeah, in reality, I mean, it's they've tried to do something really hard to drill 2 meters. So to be honest, it's not totally clear that that's going to work the way that it was initially intended, but it's a really hard thing to do. So if it doesn't, that's why. But they're going to try to do it.
Fantastic.
I was just going to ask a quick, make a quick point. I don't know if I'm coming up or not.
Yeah,
Yes.
we can hear you. Hi.
Okay. I don't know anything about about the the risk from, or the effects of radiation on organic systems. Well, I know that some of them obviously are catalyzed by UV light. But I guess the question I was going to ask was, what would be your idea, Joe, of the deepest lake that could have been present? Because obviously it's going to obviously be affected by the volume of water above the molecules.
Yeah, so there's this one lake called McLaughlin. Well, the crater is called McLaughlin, and that one I mapped it out in great detail over a period of a few years because I thought it was worth the effort. And one reason is because it appears to have been about 500 meters deep, because there are these platform sediments that give you a pretty good constraint on base level. And then we can look at the absolute depth of the lake, and at the floor of the lake, we see various things like serpentine and iron saponites and carbonates. So there were pretty clearly hydrothermal, well, what looks like hydrothermal minerals present in the bottom of that lake. And so it would have been somewhat long-lived and had a lot of nutrients available, or a lot of energy sources available, I mean. And so that's a great example. The one in Eridania Basin that I mentioned was probably at least 1 kilometer deep as well.
Thanks.
Oh, thank you. And we have 2 more quick questions. One is from Martin van Kranendonk. So what is the source of the reducing gases?
So we haven't modeled that or anything, but the idea is basically borrowing from what other people's models have shown, which is basically volcanogenic sources. But it's true that in that literature, people show the competing influences of deposition of reduced comets, cometary material, and chondritic material and things like that. So I haven't really tried to get into that game very much. I'm just sort of going by what I see in the papers, and it's a combination of both.
Okay, thank you. And yeah, Sudha Rajamani was also very interested in that question. So thanks for answering that. So with that, I'm going to thank Joe once again for a fantastic talk and for the great discussion afterwards. Generated a lot of questions, which is perfect. So thanks everyone for participating. I'm going to call the very first session to a close now. There'll be a half-hour break, and then we'll be back for more fantastic astrobiology in half an hour. Thank you all so much, and thanks, Joe.
Thank you.
Thank you to all the speakers from the first session.
Thanks.